Fort Sill, Oklahoma. Soldiers are learning to shoot sophisticated pieces of military technology. Today's big guns. These are weapons that generate and harness powerful explosive forces. This is the M777 howitzer, an important part of the U.S. Army's arsenal. When it fires, the temperatures inside the gun soar to over 4,500 degrees Fahrenheit. Its barrel directs 7,000 times more energy than an AK-47. And its shells travel more than 3 times faster than a Boeing 747. These extremes push the limits of artillery design, building on a long evolution of propulsion technology. Before artillery, there was the bow and arrow. But the bow was only as powerful as the archer who drew it.
There's a limit to how much the human body can pull the bowstring, and also the length of the human arm makes the range and strength of discharge essentially very limited.
Artillery aimed to overcome that limitation with mechanical devices. At the beginning, the goal was to increase range. (421 BC). In southern Italy, an ancient Greek force deployed a new kind of weapon against an Italian tribe. It may have been the very first artillery piece used in warfare. It was called the gastrophetes. In essence, the gastrophetes was a mechanical bow that used tension as the power source. Mechanizing a handheld weapon was a way to create more propulsive force than the human arm could generate.
A normal bow allows you an effective range of about 150 to 200 meters, and the gastrophetes probably increased that to about 250 meters.
That extra range was vital, especially against enemies that were still using traditional bows. But to shoot something heavier than an arrow, more power was required. Crossbow designer Ivan Williams has researched how ancient engineers tackled this challenge. He believes many of the early solutions may have come from nature.
You can see it on big trees. When the wind blows and they twist, then they twist back again. All those fibres, as they twist together, want to come back again. So it's a big spring. You can see that this tree here that's been split, and the fibres, as I split it, have followed it round in a curve, a clockwise curve. So as I move this arm round, all the fibres in that tree, top and bottom, are twisted tighter together, and that creates a lot of energy. That's quite difficult to pull round.
The action of twisting the tree stores up energy. This springy sapling points the way to a weapon system that would supersede the gastrophetes, one that would replace tension with torsion. Like the twisting tree, wound rope made from fibers, animal sinew, or even human hair can also generate torsion power. And rope can easily be incorporated into artillery.
What you have to do is to crank it round, turn it round, spin it round somehow, rotate it so that you're harnessing that inherent natural force, control it, and then release it at precisely the right moment.
The ancient Greeks built and tested various torsion artillery pieces in the 3rd and 4th centuries BC. British experimental archaeologists have painstakingly reconstructed one of these machines. It's called the ballista, and its throwing power far surpasses the range of the gastrophetes.
We want to throw heavy rocks, 30 pounds and more, 60 pounds. So to do that, a different power source is required. What twists it and stores the power is a steel arrangement up here with a pin that goes through the rope and then is locked into place with this pin here.
Torsion power meant that for the first time, heavy stone missiles could be shot over long distances. The Greeks invented torsion artillery, but it continued to evolve into Roman times. One of the most striking examples of its use in ancient warfare occurred in the Middle East. '73 AD, the mountaintop fortress of Masada in Israel's Judean desert. Rome's 10th Legion laid siege to a group of Jewish rebels barricaded in this lofty stronghold, which had previously been fortified by Herod the Great. More than 1,300 feet above the desert floor, Masada appears impregnable. But the Romans were able to build a ramp up to the walls and batter their way in. Key to the success of their assault was their use of torsion artillery.
This is a ballista ball that was found here during the excavations, and they were found scattered all over the area.
And in large concentrations near the breach in the fortress wall at the top of the ramp. The Roman commander, Flavius Silva, seems to have been using the artillery for a specific purpose: suppressing fire.
These weapons are not capable of battering down huge 12 or 13-foot thick walls. They are purely designed to keep people off the top of the walls so that they don't interfere with your siege preparations.
Everything was directed to one thing, to bring the battering ram on top of the ramp to those 20 meters, 25 meter wide area where they wanted to breach the wall.
Archaeological evidence suggests that as the huge siege tower and battering ram inched slowly up the ramp, Roman artillery put up a wall of suppressing fire, both from ballistas mounted on the tower itself and from positions at the bottom of the ramp. The tactic worked, and Masada fell. Artillery fire proved its value in siege warfare. But the Romans found other uses for artillery as well. They were able to adapt the use of long-range projectiles to different kinds of fighting as they expanded and defended their empire.
Technology reacts to pre-existing need. The Romans are going to be outnumbered everywhere they fight. If they're on the frontiers in Asia or Northwest Europe, the problem that they're going to face is they're going to have tribal armies that have far more combatants. You can harness technology to equal the odds so that one bolt can go through and kill 6, 7, 8, 9 people and make people so scared that they'll flee.
Jewish historian Josephus witnessed the deadly force of Roman artillery firsthand.
When a pregnant woman was struck in the belly on leaving her house, the unborn child was flung 100 yards. So tremendous was the power of that stone throw.
Artillery in the ancient world had a shock and awe value. The very visceral effects of the impact of projectile fire had a great demoralizing effect on defenders.
The effect was due in part to the impersonality of the attacks. While the dying occurred up close, the long-range strikes put the enemy out of harm's way. Victory no longer depended entirely on hand-to-hand combat. Battlefields and battle tactics were changing. At this gun factory in Mississippi, engineers are building M777 howitzers. When finished, the guns will be able to fire shells more than 15 miles. That's 80 times further than the torsion-powered ballista. But there have been many steps in between, and each new advance brought more technology to bear on the effective distance a weapon could achieve. Just as tension power gave way to torsion, so would torsion eventually be surpassed. It happened in the 12th century when a new kind of artillery appeared on the battlefield, the counterweight trebuchet. It was the most powerful weapon produced in medieval times, and its arrival ushered the ballista into obsolescence. This is Falster Island in Denmark, home of the Medieval Center. Here, craftsmen recreate many of the military technologies of the past using era-appropriate tools. Engineering trebuchets is one of their specialties. Believed to have originated in China around 400 BC, the early trebuchet was likely a simple device like this. Soldiers pulled on ropes to propel a missile from a sling. Though its route is unclear, the trebuchet eventually made its way west.
Now, when did it come to Europe? That's a real question. We really just don't know. But in the Crusades, we see the true origins of the trebuchet that we know today.
The trebuchets used in the Crusades were advanced machines that relied on mechanical counterweights to launch projectiles. It is this impressive 12th century version that experimental archaeologist Peter Vemming decided to build. His trebuchet is 72 feet high and works by releasing a counterweight that weighs as much as 4 SUVs.
When we build a machine like this one, we lack 1,000 years of experience. That's why you call it experimental archaeology. You have to try and try and try.
Ja, så må jeg gerne begynde at gå.
They also need some heavy lifting to launch it. As the human guinea pigs walk inside the wheel, they winch a rope and pulley system that slowly raises the heavy counterweight. Meanwhile, a floating target is pushed into place 400 yards away. The sling on the end of the firing arm shoots a 33-pound stone ball.
Short a few feet, about 20 feet to the right.
The shots come very near the distant target. And lack of a direct hit isn't the drawback it appears to be. In the Middle Ages, the trebuchet would have been aiming at or over wide castle walls. They would also fire iron and flint-filled projectiles that shattered into lethal fragments upon impact. Accounts from the time suggest that sometimes the machines were used as much for effect as for damage.
We get these stories of them launching things over the walls.
Barrels with oil that they could ignite.
The heads of their enemies that they'd captured to scare the people inside.
We even have sources that tell us that they sent back captured spies, enemies, and you knew they were landed when the cry stopped.
In some cases, just the threat of a trebuchet attack could be decisive.
The best siege is the one that's not fought. If you have this big, huge device that launches things over the walls and into the walls, and the sound is incredible, and fires start, and people are going to say, we've had it. We're surrendering now. It's done.
But of course, not everyone surrendered, and fortification engineers found ways to fight back. One was by building castles with multiple levels. towers and concentric defensive walls of immense width. In the bitter Crusader battles of the 13th century, these castles resisted trebuchet attacks. So generals needed a new tool in the ongoing struggle between offense and defense. They found it in the form of gunpowder, one of the most important inventions in the evolution of warfare. France, 1324. The city of Metz was under attack from feudal lords. Though the battle itself was minor, it is remembered as the first recorded use of gunpowder artillery.
From then on, we realized that nothing's going to be the same. Gunpowder weapons of large caliber, of small caliber, big, huge guns, smaller guns will all have a great impact. And it's not long before trebuchets are gone. It's not long before archery's gone, crossbows, everything will change.
Not just from the introduction of gunpowder as it made its way slowly from China, but from its marriage with the barrel, which allowed engineers to direct the force of the explosion. The challenge came from the strength of the blast. If the barrel wasn't strong enough, it would be torn apart when the gunpowder went off.
When you're developing something new, you try all sorts of things. You would have tried anything to hand, and of course, at an early stage, you might have tried bamboo.
This 10th century Chinese illustration shows Buddha being attacked by a demon wielding what looks like a gun barrel made from bamboo. Armorer Scott McIntyre has designed his own version of the demon's fire lance.
Here I have a typical projectile, which is actually a papier-mâché ball, and behind that there's a gunpowder charge. If that is actually inside a tube, when this charge is ignited, it will build up an awful lot of pressure.
McIntyre's tube is a hollowed-out piece of bamboo.
That's pretty much there now. There's just a few more small pieces, but yeah, that looks pretty good.
The barrel must be securely strapped down before it's fired.
The projectile will be loaded in down to here. There's a bung in here which will then contain all the gas. As it expands, the projectile will travel down the barrel, exiting the muzzle here, and hopefully reach our target over there.
The bamboo gun fires as planned, but even with the target less than 160 feet away, it's not very accurate. It takes 5 shots to hit the bullseye. It's a start, but not yet the effective weapon explosive artillery will become. Today's artillery barrels must withstand incredible stresses. Before any new artillery piece is declared ready for battle, its barrel is put through a series of mandatory tests. The tests take place here, in the Arizona desert, at the Yuma Proving Ground.
All stations, stand by for a 5-second countdown. Tube round number 45 in 5, 4, 3, 2, 1.
Each M777 has to perform at the maximum pressure the gun barrel is designed to withstand. The ammunition is loaded at the rear or breech of the weapon. The projectiles used in the test are the heaviest and most explosive the gun can handle and generate the hottest temperatures. The barrel can withstand these forces because it's made from a single solid piece of hardened steel. But that effective single-piece construction evolved from many earlier and not always successful gun barrel designs. July 19th, 1545. The Mary Rose, flagship of Henry VIII, sank off the coast of England. This cannon is from the wreck.
What's really wonderful about this piece is because it sat on the seabed for so long, what's happened is parts of the surface are completely corroding away, revealing the structure inside. It's made of long strips of iron, which we call staves, which you can see along the top here, and they run the whole length of the barrel. And around it, they put rings and hoops of iron.
The corrosion reveals a construction similar to that of a wooden barrel. The kind that would hold dry goods or beer. In both cases, the hoops apply pressure from the outside to keep the staves together. The gun barrel simply replaced the wooden staves with iron. But whether using iron or wood, there is an inherent flaw in the design. When this experimental hoop and stave gun is fired, explosive gas leaks out between the staves. This saps the power of the explosion and can be disastrous for the gunner.
Every shot had the potential to explode the barrel and kill all of those standing around the weapon.
What you're really looking for is a material, a piece of artillery which is a very good, solid, continuous piece of metal.
The skills to make such a barrel came from traditional craftsmen who created far less violent items, bells. At this foundry in Loughborough, England, founders cast bells in the medieval way by pouring molten bronze into a mold. In 14th century Europe, this casting method was adapted for gun barrels.
All you've really got to do is make a different form of mold. You already have the furnace, the technology and the knowledge of bronze to do it.
By the mid-15th century, huge barrels could be made from single pieces of bronze.
Gunpowder artillery has diversified, both in size and power, in purpose, in metallurgy. People are starting to understand, generals and leaders are starting to understand how valuable guns are.
1453, Constantinople, in what is today Turkey. The Byzantine capital city was under siege from Ottoman Turks, who were expanding their empire.
By the beginning of the 15th century, the Ottoman Turks were actually behind in gunpowder weaponry. But by the middle of the 15th century, they're above everybody. It's as if they got this incentive to build guns and build them of enormous size.
Big guns that the Ottoman Sultan Mehmed II unleashed against the walls of what was then the greatest city in the world. Guns like this.
This great Turkish bombard was cast in 1464 for Mehmed II, the conqueror of Constantinople. This is the breech chamber, which contained the gunpowder, loaded in here and held securely by a wooden plug that would be hammered in, would help to build up the pressure. Then the two halves are brought together, and with huge effort, using wooden spikes in these recesses, the barrel is screwed onto the breech.
The breech section alone weighs a stunning 8 tons.
So the barrel's already been screwed together. It needs to be loaded with one of these massive stone granite cannonballs weighing over 600 pounds.
Bombarded for nearly 2 months by these heavy projectiles, entire sections of Constantinople's walls collapsed. The city fell, and military leaders around the world took note.
The fall of Constantinople was a major watershed, not only in political and economic history, but in the history of military technology, in that it showed that even the most powerful, thickest walls could be brought low by gunpowder technology.
Artillery once again held the upper hand over fortifications. But there was still a dangerous flaw in the design of the gun barrels. Casting technology had made them stronger than hoop and stave, and eliminated the leaking gas. But they had a frightening tendency to explode when fired.
Before around 1470, cannons cast in bronze were cast with the breech of the gun, the back of the gun. They were cast vertically, and the breech was at the top and the muzzle was at the bottom. The problem was, when you poured it with the breech up, the impurities tended to gather at the top. So, of course, the impurities, the gaps, were in that part of the gun where the explosion happened. So you always had inherently weak guns. What someone realized you could do is you could turn your cannon over, and you now cast it with the muzzle up and the breech at the bottom. So the best metal, the best casting now, is at the bottom, at the back of the cannon where the gunpowder was.
Such a simple change made a world of difference, and it came at just the right time. For gunpowder was also being improved. By mixing the ingredients wet instead of dry, powder makers in France were able to change gunpowder's consistency and create a more stable and powerful burn. The new method was called corning.
When you have grained powder like this, the first grain to ignite generates a flame which shoots between adjacent grains. What this means is you can get powder that burns seriously fast.
The trail on the right is filled with gunpowder as it was made in the early 1300s. The one on the left contains the newer corned powder. When the two trails are lit simultaneously, the difference is clear.
Firing! 4, 3, 2, 1.
The corned gunpowder burns down in just 3 seconds. The earlier formulation takes a full 41 seconds to burn itself out.
When you got to corn powder, you had really good high explosive, which you could then develop a better cannon for and get longer ranges and better smashing power.
The gunpowder was more explosive, the barrels were stronger, and the projectiles too started to improve as stone cannonballs were gradually replaced by iron.
When they did develop the idea of cast iron, it obviously was the ammunition to use, because size for size, cast iron is 3 times heavier than stone.
It's not going to shatter when it hits a hard fortification, and it travels through the air more efficiently.
Heavy metal soon became the standard for artillery projectiles. Packing all that punch is wasted, though, if the projectiles miss the target. So a great deal of modern artillery training concentrates on accuracy.
We're a precise organization, and we deal in precision. We, as artillerymen, measure many aspects of what we do. We measure the muzzle velocity, the speed at which the round departs the tube. We measure the weather so that we take into account for that. We measure the accuracy of the target so that we know exactly where that is.
Stand by. Fire.
This quest for precision and accuracy began in earnest in the 16th century Italian town of Verona. Poking out of a cannon muzzle, this gunner's quadrant is the product of Renaissance innovation. It was invented by Niccolò Tartaglia, a self-taught Italian mathematician and the father of ballistic science.
What Tartaglia did was he took the subject of gunnery from being a bit of a black art. He brought it into the light of Renaissance science, and he tried to see why the cannonball flew the way it did.
Tartaglia came up with a mathematical theory for the flight of a cannonball fired on a flat trajectory with 0 degrees of elevation. And he did so 120 years before Isaac Newton made his discoveries about gravity.
There was no developed theory of gravity in Tartaglia's time, but what he realized was that the cannonball would start to fall from the muzzle of the gun as soon as it was fired.
He also worked out the angle of elevation needed to achieve maximum range. At 0 degrees, a shot fired from a cannon quickly falls to earth. Raise the barrel to 22.5 degrees, and the shot travels in an arc, improving its distance. Double that to 45 degrees, and the shot reaches its optimal flight path. These calculations led Tartaglia to invent the invaluable gunner's quadrant.
The gunner's quadrant allows you to set the angle of the gun to a particular elevation to control the range, and you read it off with a plumb bob. As the barrel is elevated using hand spikes, you'll see the plumb bob move.
Adjusting the wedges under the breech of the gun causes a change in the barrel's elevation.
Of course, the plumb bob is really staying vertical because of gravity, and the barrel is moving the scale up and down.
The result is improved accuracy and the ability to methodically adjust the angle of elevation to home in on a target. The next major advance in artillery design would not arrive until the Industrial Revolution, 3 centuries later. It was then that machine tools allowed for the mass construction of precision, rifled components for both muskets and artillery pieces. The result was greater accuracy and deadlier strikes. American Civil War battlefields became the testing grounds for the new technology. Antietam, Maryland. In September of 1862, this was the scene of the bloodiest day in American military history. A day when rifled guns and artillery contributed to the killing and wounding of almost 23,000 men. Soldiers who survived the fighting documented the devastating effect of the rifled artillery.
A converging storm of iron slammed into the batteries, from front and flank. Wheels were smashed, men knocked down, horses sent screaming.
By the middle of the Civil War, we're seeing many rifled guns come into place. Now, what does rifling mean? It's a series of grooves that are cut into the barrel. And those grooves, if you were to look down the barrel, actually turn. Why? We have a new type of projectile.
High-speed footage of a modern artillery shell shows how these new elongated projectiles behave in the air. This one is traveling at 2.5 times the speed of sound. Like a football, a shell fired from a rifled barrel spins in flight, significantly improving accuracy.
Your projectile is going to come out of this barrel, properly fitted, and it is going to continue in a perfectly straight line to its target as it spins, holding its stability the whole way.
At Antietam, the Union troops had twice as many rifled artillery pieces as the Confederates. When these more accurate guns engaged the Confederate smoothbore pieces in the Dunker Church area, they took a terrible toll.
The Confederate artillerists actually refer to that battle as artillery hell. And this is where the opposition of smoothbore and rifled cannons really shows itself in its deadliest possible form.
A simple shooting competition reveals the difference between the rifled gun with elongated projectile and the smoothbore barrel with ball. These targets have been positioned 150 yards from the dueling cannons. First up is this Napoleon smoothbore, an original piece from the American Civil War.
Fire!
The smoothbore's round shot seems quite accurate at this relatively short range. But after 5 shots, there have been no dead center hits. Next up is this 1861 Parrott rifled gun, shooting the elongated shells that spin in flight.
Fire!
Wow.
Move!
After 2 shots, the rifled gun is already demonstrating its superiority.
Fire!
Ha-ha! Right down the ball. Exactly down the center. Perfect dead center bullseye.
During the Battle of Antietam, the rifled artillery showed similar lethality, handily outgunning the smoothbore guns with deadlier accuracy and greater range.
Civil War battles would have taken place using this type of munition at 600, 700, even 1,000 yards. And at that point, this circle becomes much, much larger, possibly as large as 20 feet, which means these may have missed their target entirely. Think of it this way. You have 2 cannons opposing one another. One is a smoothbore, one is a rifle. They're trying to knock each other's guns off their carriages and silence that artillery piece. This gun could put that gun out of commission, and they could not return fire accurately enough to stop them.
The Industrial Revolution had made artillery deadlier than ever. Next, it would once again change the material from which gun barrels were made. This 1943 artillery piece is being decontaminated and cleaned up for display at the U.S. Army's Ordnance Museum in Maryland. A powerful pressure washer effortlessly removes the old paintwork to reveal the original metal underneath. Steel.
Steel has immense tensile strength, and you can also heat treat it. You can do all sorts of things to steel to make it the ideal material for building gun barrels.
But up until the mid-19th century, producing a block of steel big enough and with enough tensile strength for a gun barrel proved daunting to manufacturers.
Steel, to start with, is not a metal that can be used for gunnery. They made barrels of steel and they burst.
Until 1847, when a German steel factory developed a new way of casting steel by adding in nickel and manganese alloys. The result was steel strong enough for a big gun barrel. The transition to steel barrels essentially brought artillery into modern times. Accuracy, range, and firepower had all been mastered. But there was still one major area to improve: rate of fire. For this, engineers needed to harness the gun's recoil.
Button. Stop.
Clear?
This machine is testing the M777's recoil system.
One of the major problems with artillery was that every time you fired it, you'd have to put the gun back into position after firing because of the immense recoil that was produced.
When the M777 fires, massive forces are generated. Without a system to counter the recoil, the gun would jump several yards backwards and out of position. Realigning it would take valuable time. In the 1890s, French military engineers overcame the recoil problem with a truly revolutionary piece of artillery. This is it. The French 75mm field gun. This original from the 1920s performed ceremonial duties at the U.S. Army's artillery school at Fort Sill, Oklahoma.
This is the grandfather of all modern artillery.
We wanted a much faster frequency of fire, a more efficient cannon that didn't need to be repositioned after each shot. So it was with this in mind that the French artillery developed a new cannon, the 75.
The gun had to be designed in secret. Germany, a rival military power in the second half of the 19th century, had sent out spies to gather information on other countries' guns. But the French director of artillery was one step ahead of the Germans.
He organized a series of firing tests, knowing full well that the German spies would be there to see what was going on.
But the guns on display were missing one vital component: their hydropneumatic recoil system. When the real gun fires, a piston drives through oil in a cylinder, dampening the recoil. In a second cylinder, the oil compresses nitrogen gas, which drives the oil, piston, and barrel back to their starting positions. Before the French 75, the average rate of fire for artillery was 10 rounds per minute.
A gun team with the French 75 upped that rate of fire from 10 to 20 rounds a minute. It is a phenomenal gun.
The French 75 had a rifled steel barrel. It was lightweight and mobile, but robust. It even had a steel gun shield to protect its crew.
When we look at this gun, and we consider it against the problems that have faced people over the years of making gunnery, everything is solved in this gun.
By the outbreak of World War I, the French 75 was the main field artillery piece for both France and the United States. (1914), the Western Front in France. The use of artillery in this war would transform combat forever.
Artillery comes into its own in World War I because the pieces are finally big enough to have a real dramatic impact on the battlefield.
Both sides tried the artillery barrage as a means of breaking the stalemate of trench warfare. As a tactic, the barrage had been established at least a century earlier in the Napoleonic Wars, but never had the world seen numbers like these. They fired further, faster, and more destructively than ever before. The mass bombardments began and ended at prearranged times, clearing the way for infantry to follow.
Only the artillery can flatten enemy barbed wire. Only artillery can destroy the trenches. Only artillery can destroy enemy artillery. So everything in World War I is going to fall on the artillery.
What began in the Middle Ages with the trebuchet had now reached an apex of efficiency. Artillery had become the driving force in ground warfare.
These shells that they're firing could explode into 1,000 pieces. These shells that they're firing could be airburst shrapnel shells that pepper the ground with burning pieces of lead.
1 million shells were fired in the first week of the Battle of the Somme in 1916. That's 1 million shells fired by the British alone on a 14-mile front. Thousands of Germans were killed in that initial bombardment.
Much of the killing that's done in World War I, the people doing the killing don't know who they're killing or even if they've hit anything at all because the killing is being done from such a distance.
Battles now took place over miles rather than yards. For the first time in history, artillery was the greatest killer in war. By the end of World War I, 70% of the total casualties had been caused by big guns. And just like their medieval predecessors, World War I generals realized these weapons could be used not just to kill, but to terrorize. Germany's Paris guns were monsters. They had barrels 130 feet long and needed crews of 80 men to fire them. In 1918, they shelled the city of Paris from 75 miles away.
To build a weapon which will fire a shell weighing about a ton that far consistently is incredible.
To shoot a projectile so far, German scientists had to factor in the rotation of the Earth and the curvature of its surface. The shell's trajectory at 45 degrees took it into the stratosphere, where the thin air caused little resistance. This allowed it to travel even further. The World War I Paris guns were roughly twice the size of this German World War II railgun. Though they caused fewer than 900 casualties, the Paris guns terrorized the Parisians when they were fired.
In strategic terms, the Paris gun was a flop. In technical terms, it was a brilliant success.
Lessons learned from the flight of the shells also proved invaluable in World War II. They were put to use in the Nazi V-2 rocket program of the 1930s.
There's no question that the V-2 rocket was not only the world's first strategic ballistic missile, it's the world's first space system.
The V-2s created an entirely new arm of artillery warfare, and ballistic missile technology became the catalyst for the Cold War arms race between the US and the USSR. Missiles, which are in effect self-powered artillery shells, could travel to every corner of the globe. No gun barrel was needed, and there was no place on Earth beyond their reach. But even before range became a non-issue, some engineers were switching their focus from distance to pinpoint accuracy. October 1944, World War II, Leyte Gulf, the Philippines. Japanese aircraft attacked U.S. ships with devastating effect, but American scientists would soon counter the kamikaze raids with a new artillery invention: the radio proximity fuse, a first-generation smart weapon.
Now, the way this thing works is it has a small radio transmitter and receiver built into it on one unit. And it sends out a signal, and when that signal is bounced off a solid object, a receiver will pick that up.
When the transmitter gets close enough to the object, it triggers the shell to explode. The radio proximity fuse had an enormous impact in the Pacific, helping U.S. ships shoot down many enemy aircraft. It was a sign of things to come in the decades and conflicts that followed. Advanced electronics would start to make weapons smarter and capable of performing many of the tasks previously performed by their crews. The M777 has a computerized fire control system that enables the gunner to calculate all the parameters needed to hit a target. This weapon takes electronic automation to an even higher level. It's called the NLOS cannon, and it's a realization of the centuries-long quest to control range, accuracy, and firepower. In our digital age, it also aims to minimize the possibility of human error at every stage of firing. It's a prototype 155mm self-propelled gun that could soon enter service for the U.S. Army. The NLAWS is being readied for testing at the Yuma Proving Ground.
Traditional gun systems had men in the back that had to lift 100-pound projectiles, lift 20 and 30 pounds worth of propellant, had to do it under very arduous conditions, hot, cold, raining, snow, etc. We've now taken those manual tasks and put them into the hands of machinery, which does it repetitively, always doing it right, never having a failure.
Automation is the innovation. Ammunition handling, loading, and the firing of the gun is all done by machine. Where the Paris gun had a crew of 80, the NLAWS needs just 2.
These soldiers now have the ability to fight the battle and not be fighting a machine. They're looking at what's going on around them. They're looking at what their commander's asking them to do. They're looking at the terrain. Instead of worrying about, is the next round loaded? Is the next round on board? I have a machine that does that for them.
Artillery has been part of war for 2,500 years. In that time, its range, accuracy, destructive power, and technological capabilities have reached ever higher levels. Time and again, artillery has transformed the way battles are fought, moving gunners farther and farther from the kill zone, and changing the dynamics of war as we know it.